Hi all, Mads Barnkop from Kaizer Power Electronics here. Today we're taking a look at this huge Fluke Helios Plus 2287A Data Acquisition Frontend, and it comes with a 2281A extender chassis. Now, what is a Data Acquisition Frontend? Well, it is a system mainframe built solely around being connected to a host computer or a terminal, and this just is a command response piece of equipment. It's a huge data acquisition set. It can do digital I/O, it can do analog output, all kinds of analog inputs, and this is configured up to 200 inputs of real-time RTD thermocouple temperature measurements. So let's check out the back of this. It is all highly configurable with different cards that you can insert into this mainframe unit. I guess there's something like 10 to 12 different cards. We have the main unit down here with the power supply, and also has all the serial interfaces, which can connect up to 15 of these extender chassis, which means the whole complete system here can go up to 1500 IOs at once. Now it has a high performance AD converter sitting at top, which is the option 161, and then it has RTD input connectors 177. 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's 20 inputs per card. So we are up to some 180 inputs here. Also up here we have the same high performance AD converter input card in the extender chassis, which would then connect via the serial bus, which has been cut off here. This is the connector out to the host PC. The different cards in the mainframe just slides out, sits with 2 screws, and you can just pull them out. So this is the high performance AD converter, which is a 17-bit piece of card. It's all shielded, and the high performance card here is also described as being good to being used in noisy or high voltage environments, so that would explain the extra shielding. Now the thermocouple connectors here, they are just that, a connector. So it just describes how you would connect your 4-wire, 3-wire thermocouples. And then you can open up the lid here, and it's just a row of connectors. So as we can see here, external RTD has been connected, but we also have some neutral points here where it's just resistors mounting in the terminal. Alright, so the connector card didn't just come like that alone. It also has a what connects the inputs down to the mainframe backplane as well. Just look at that. Copyright 1982, John Fluke Manufacturing Company Incorporated. That's just awesome. Looks nice. It's very hairy. And also vinyl cladded, as described in the manual, that the whole chassis is vinyl cladded, but also apparently on the back of this PCB. But what we have here seems to be current transformers, that the measurement is being converted through these back to the analog to digital conversion into the back plane. It does, however, seem like we have some moisture damage up here, so that's a bit of a shame. So it is definitely not current transformers. These are read relays. So that's actually, now we know how this unit works. It says here, read change, the 4th of May, 96. So each channel is being read out in a sequence, and that's how it works. That's how we can go up to 1500 channels on a serial link. The mainframe assembly is almost completely empty. We can see the back plane back there, and we can now pull out the main power supply and computer here. And it's clear that we have the power supply sitting at the bottom here, and we have the CPU card at the top. So let's get this taken apart and taking a closer look. The main computer part here is really interesting because we have some brand names and some names on these parts that I have not seen in a very long time, and which have some interesting stories behind them. Now over here, the power supply. Besides being a switch mode power supply, and it looks just like any regular one, 1984 Borchert power supply. Now, Borchert, that's an interesting company when it comes to power supplies, because it was founded by Robert Borchert in 1970, around there, where he quit his job as various large electronic manufacturers to make switch mode power supplies. He is one of the main drivers attributed with the low cost, high volume switch mode power supplies being put into the market. Until then, it was really just custom jobs, and he made a living out of making switch mode power supplies for suppliers like HP, Sun, and the US military. So really interesting to see a piece of power supply history sitting in this piece of equipment. I'm not quite sure there's much to say about it. It probably delivers 3 different voltages from the 2 to 3 regulators sitting here. Over here from a full bridge we have some capacitance, we have 2 switches, we have a large transformer with multiply outputs here, and then we have some various regulators near the output. Now let us not forget that doing electronics is all about getting a nice mug of hot coffee here in the high voltage mug, which you can find in my merchandise shop. And since it's Christmas, also some nice Danish homemade butter cookies. Made by my wife. Very, very nice cookies. Alright, I said this was also a very interesting computer interface assembly board. And what makes this interesting is the main CPU, which is a TMS 9995 Texas Instruments single computer chip. And that is the TI 990 mini computer, which has been put down into a single chip. This was done in 1976 with the first version 0. This is of course a later version which sports up to 256 bytes of RAM and runs at 12 megahertz. So let's just zoom in on the board itself. It's quite clear that we have some EEPROM sitting up here, and we have some external RAM as well. It does not feature any ROM in the chip itself. We have a lot of CMOS logic sitting around here, and that is actually what makes up the serial interface of up to 1,500 IOs. That's quite incredible. Now, the history about the TMS 9900 series CPUs, or single computer chips here, is that they were beat on the personal computer market by the Intel 8088 and also the Intercell 6100, which was the single computer from the very famous PDP-8 personal computer. Now, the TMS chip from Texas Instruments does ring a bell if you have seen my previous videos on base station amplifiers for mobile phone networks, because this developed into the TMS 320, and that was specialized into special purpose DSP products and has ended up in a lot of base station amplifiers for the 3 and 4G generations of the networks. Very interesting CPU card. This is the high performance AD converter assembly board. It's marked copyright 1983, and we have a EEPROM sitting in here, setting copyright John Fluke 1992. So it is a fairly old design by the time that this has been sold. Now again, we have a lot of CMOS ICs sitting around, and then we have a EEPROM with a specific program, and we have 2 large controllers. Now, the high performance does not refer to the speed, but more to the precision, as this is a 17-bit precision analog to digital conversion. It's running off a Toshiba TMP 80C39AP6, which is a 6 MHz from the crystal next to it. It is a fairly specific controller IC, which has running on 8-bit with 1 kilobyte of RAM, 2 kilobytes of ROM. It has up to 27 IOs and 8-bit timers. So it's made for something like this, with synchronizing a lot of different signals back into the HD36402, which is a 2 MHz UART. Now, this is a UART is of course a short for Universal Asynchronous Receiver Transmitter. So this is the whole high-speed interface back into the backbone, which those 15 extenders can actually run on. So they communicate all of them through this. There is no local computer in the extenders, so that's a part of the high-performance AD converter assembly. I found a little funny thing here on the high-performance HD converter, which is these two components here, which has different numbers on them. Usually I would know these as resistor arrays or something like that, but I'm not quite sure what that is, if that's some kind of specific configuration to avoid copies of the hardware. Let me know in the comments if you know what those are. On the back of the high-performance AD converter board, there's a few funny features among the routing of the signals. Now check out this track here, comes up here, splits into two, and then continuously parallel all the way out to the connector at the back of the board to the back plane. That's quite interesting. Another funny feature we have here is we have 4 transistors sitting in a row here, actually 5 I think. But we can see here we have a board connector from the ground plane, and then it has a track all around these 5 legs going back to that. So what we're seeing here is actually noise protection, that we have guardrails of grounded tracks all around very sensitive circuits. And we can also see up here where we have where it's just screwed down into the shield of the connecting plate. That's also grounded all around that mounting screw. So a lot of very classic routing in this board, but also some small funny details like these guarding grounds. The input cassette here, not much to say about it, except that it's a fairly okay layout, that we have these terminals shifted back and forth, so you actually can see the markings down here, channel 9, channel 11, channel 10. So you don't get confused with which channel is which when it just sits in one long row. So actually a good enough layout, actually with that in mind, that you get your cables in, and it's actually mounted up towards the middle here. So you get your cables in and you can put it in nicely. So fairly well thought layout for something that you need to change a lot of time, because this is made for experimental setups. Now the read relay readout back connector here to the front connector, not too much to say about it. Has again CMOS logic and seems to be just feeding out data, and it's the high performance AD converter that has to do all the job. This is just a timing circuit that switches in the different channels that it has to read out. Interesting to see, however, is these Fluke marked precision components, which has gold legs. But we can zoom in a bit here to see the layout a bit closer. That seems to have a transistor for each channel that switches around the different read relays to drive those, and then we have just CMOS logic to take care of the timing circuit, and we have of course diodes to take the switching transients when turning on and off a relay. Now why would you make it with read relays like this? My main guess is that it's fast and low noise, and maybe just a lot cheaper than using switching silicon components. Might also have something to do with noise issues, that these are probably very good shielded up on this, kind of weird assembly sitting up here. We can see it's a pretty thick assembly here, and it seems that there is a lot more underneath there. So yeah, I'm not quite sure why the designers chose read relays. Maybe that was just the choice of components and technology at the time of design. But let me know in the comments if you have a better explanation. I got the board cleaned up, washed the main CPU card over here in mild soap with an old toothbrush, and then dried it out at the heating panel, so a good 50 degrees Celsius. Cleaned out the power supply. That was not that dirty, so I could clean this out with a dry brush. I located the ground to be wire 2 here, according to the main DC capacitor over here at the CPU board. So let's try to plug in the power supply and then measure the voltages before putting the whole unit back together. Now before we put it back together, I also did check on the dip switches that it's set up for all its default values for serial communication. So yeah, let's just plug the power supply in, turn it on. And as expected, that's a bit noisy. So let's check out the voltages. We got 12 volt for the fan. Got a 5 volt on pin 1. 12 on 3. Minus 12 on 4. 5 on 5. Probably a ground again here. 12 and 12, minus 12. So it seems like it has 2, or maybe just it's dual, but at least we have 5 and 12 volt DC power supply. So let's hook it back up together and start up the unit. The original serial connector here was a bit busted up and rusty, and yeah, that is just a serial interface. So I went through all my old serial cables and came out with this amount of connectors and cables in order to get from a normal serial cable and to the female DP25. And then I also put a RS232 check tester in the middle. So let's get it hooked up and see what we can get. I'm using one of my first laptops here with the Realterm, which is a serial capture program. Now we have to set up our serial port, which defaults to 9600 baud. It was non-parity, 8 bits, 1 stop bit, no hardware flow control. Let's just open that port and then turn on the unit. Alright, we immediately got some response from it. So we need to just set that up. Now I found some just some commands from the manual, so let's try out those. But first we have to tell it that we want to use it in terminal mode. Okay. The answer is HCLI. Then the next thing you can do is send a version check on it. Oh, how nice! Helios Plus version 3.3, software by John Fluke Manufacturing Group Incorporated. Or Manufacturing Incorporated. How nice is that? What else can we do? I also looked up to do something with the 163 resistance measurement cards that were the backplane cards, and for that there were some listed tests. We have to set the format to decimal, and we have to define all the channels, as there is no definitions in this. There was no backup battery on the high performance card, which means it doesn't remember anything between powering on and off. And we tell us its resistors, max 100 ohm. And then we should be able to make a readout. Send channel 0 to 19. So let's read out the first 20 channels. There we have it. Actual resistance measurements from the unit. How nice is that? And what a lovely sound it makes. I'm not even sure I can capture that on microphone, but that fan is pretty noisy, but I'll give it a try. I'll stick the microphone near the unit now while we do a readout, and we can actually hear the read relays. So 3, 2, 1, now. I hope you heard it. So before turning off the data logger and finding it a new home, let's just do a last readout. Here I do all 100 channels with 20 repeats. So let's just make that run here in the laptop in the background. It takes it about some 5 seconds to read out all 100 channels. So quite fast for so many channels at once for a piece of equipment of that age, and also that versatile. So it was a really nice piece of modular equipment to take apart, clean out, not much repair to do, luckily, and it just works again. And all I can say now is thank you for watching. I hope you enjoyed it, and until next time, see you.